All right, hello everyone. Welcome back to another lecture. So if you remember last time we talked about rotation matrices and how they are useful in terms of transferring or calculating components of a vector in a new reference frame given its components in another reference frame. Well, today the first thing we're going to have a look at is how can we practically calculate that rotation matrix. And the idea to do that practically is through the use of principal rotations. So we're still within section 1.3, but now we're going to look at 1.3.2 and specifically at principal rotations. So there are actually three principal rotations out there. The first one is a rotation about the x-axis of a reference frame. The second one is a principal rotation about the y-axis. And the last one is obviously principal rotation about the z-axis of a reference frame. So if you know the sequence through which you can go from one reference frame to another reference frame by these kind of three-step principles. So, for example, to go from reference frame A to reference frame B, if you first rotate about X, followed by Y, and by a third rotation about Z, then you have all the ingredients to be able to calculate that rotation matrix. But the order could be whatever. It could be a principal rotation about Y first, followed by a rotation about Z, and you end with a rotation about Y again, something like that. But first, let's define those three principal rotations that exist. So the first one is Cx, okay? So Cx denotes a rotation about obviously the x unit vector of any reference frame, like that. And that rotation that takes place about a single axis at a time, the x-axis in this case, will be done through an angle denoted theta x. All right? So that would be the situation where you have, say, reference frame A oriented like that, AX, AY, and AZ. And then you have reference frame B that is obtained from A through a single rotation about the AX direction. So that would be the axis of rotation in a way. So you would get BY around here. Oh, sorry, that was AZ, obviously. You would get BZ like this. And because AX was your axis of rotation, it means that AX and BX coincide with each other, like that. And the rotation is performed about AX only. So you take your reference frame A and you spin it about its AX direction through some angle theta x, and then you get the reference frame B as a consequence of a principal rotation about X only, okay? So the angle theta x would be here and would be here as well. Whenever that is the case, it means that the rotation matrix that relates reference frame B to reference frame A is obtained or is calculated by a 3x3 matrix that has the 1 in this upper corner, followed by one row of zeros and one column of zeros. And then you have cos of the axis or the angle of rotation about that axis. Here you have sine of this angle of rotation, and here you have minus sine of that angle, and finally cos of the angle of rotation in this position of 3x3 rotation matrix, okay? So instead of trying to figure out and measuring all angles and things like that, if you know that B is obtained by a single rotation about the x unit vector, then you can apply that directly to find your answer. So that is a principal rotation about the x direction, okay? But you also have two other principal rotations that exist. The second one is a principal rotation about a y unit vector. And this one will be denoted as cy, function of theta y. So that is the angle through which you rotate to obtain reference frame B given a reference frame A to begin with. So graphically, it would look something like this. So you have your initial reference frame, AX, AY, AZ. And then you obtain reference frame B about a single rotation about the Y axis here. So you spin reference frame A about AY, and then you're going to obtain reference frame B, BX, BZ like that. And because Y was your axis of rotation, it means that AY and BY are on top of each other like that. And the angle of rotation in that case is simply denoted by theta y. All right? So whenever that is the case, you can directly write that the rotation matrix that relates the orientation of reference frame B with respect to reference frame A is a 3 by 3 as per usual. That looks like this, where here you have cos of the angle of rotation about the y-axis minus sine theta y, sine theta y in this position, and finally you have cos theta y in that position. Okay? So again, that is the answer for your rotation matrix, or in other words, how can you practically calculate that rotation matrix if you want to go from reference frame A to reference frame B, knowing that the relationship between those two reference frames is a single rotation about the y direction. Okay. And lastly, you're going to have a look at the third principal rotation that exists. And that is principal rotation about the z direction. And this one is denoted by CZ, function of an angle denoted theta z. So graphically, it would look something like this. You have your initial reference frame, AX, AY, AZ. And now what you do to obtain reference frame B from that initial reference frame A is that you rotate it through AZ. Okay? In that case, if that is your angle of rotation, again, it means that AZ and BZ coincide. That BY will be separated by an angle theta Z from AY, and that BX will be separated by an angle theta Z from AX, like that. If that is the case, if reference frame B is obtained again by a principal rotation about Z only from reference frame A, the answer for your rotation matrix is going to be a 3 by 3 matrix, obviously. That would look something like this, where now you have cos of the angle of rotation about AZ, followed by sine of this angle. Here you would have minus sine and finally cos theta z. Okay? So that will be your rotation matrix if this is the situation you're dealing with. Now, in the most general case, though, a reference frame isn't obtained by a single principal rotation given another reference frame, but is obtained, as I said previously, as a sequence of principal rotations, one after the other. So in the most general case, when we're talking about 3D space, a reference frame is obtained by three principal rotations that are stacked on top of each other. Okay? And this is how we're gonna have a look at next. But first, we needed to understand the building blocks of a three-step rotation. So three principal rotations, one after the other, to be able to get the resulting rotation matrix. So we're still within 1.3.2. So let's pretend that you have the initial reference frame, which is denoted as A, reference frame A, and ultimately, after three principal rotations, we finally obtain reference frame B. Now the question is, how can you calculate the rotation matrix relating the orientation of reference frame B with respect to reference frame A? Well, to do that, you need to know the order about which you rotate to go from A to B, okay? So that is the starting reference frame, and that is the end reference frame. So let's assume that we do the classical sequence denoted as 3, 2, 1. So in aerospace engineering, the 3, 2, 1 rotation sequence is one of the most popular ones. It's kind of the standard or the norm whenever we talk about principal rotations, when you have one stack after another one, up to 3 consecutive rotations. So this is a very popular rotation to relate one reference frame to another. So 3, 2, 1, first you need to understand what it means. 3 means this is a rotation about the third unit vector of a reference frame, i.e. this is your CZ that we talked about. 2 means that you are rotating about the second unit vector of a reference frame, or in other words, this is your CY that we looked at previously. And finally, you have 1 in the sequence, and the 1 here means that you are spinning about the first unit vector of a reference frame, and that is the X unit vector, and therefore this is your CX principal rotation. So the sequence 3, 2, 1 means that you are rotating about Z, rotating about Y, and rotating about X. Okay. So the way it looks is that you first go, it's a three-step process. So first step, we say that we go from reference frame A to some intermediate reference frame that we're going to call A prime. And to do that, we're going to use the first rotation in the sequence as a label, or as given to you. In this example, this is a third rotation, so C3 or CZ, it's the same thing. So CZ by an angle theta Z. So that is the first step of the three-step rotation sequence. You take your reference frame A and you spin it about its Z unit vector by some angle theta Z, and you end up with some other reference frame denoted A prime. Now in the second step, you start with what you had as a result of the first step, which is your A prime reference system. And then you're gonna end up to another intermediate reference frame denoted as A double prime. And the second step, well, you have to refer to the sequence given to you. And the second step of the sequence is 2, meaning that this is your CY principal rotation that we talked about through an angle theta y. And the third step of the entire sequence, rotation sequence, is to go from A double prime to finally the result in terms of reference frame, which is the B reference frame. And according to the sequence, the last principal rotation is CX through an angle theta x, like that. Okay? Now that's all good, but how does that help us calculating the rotation matrix that relates the initial reference frame, FA, all the way to the end reference frame, which is the B reference frame? Well, again, given the sequence 3, 2, 1, it means again that the first rotation is CZ, followed by a second rotation CY, and the last one, because you have 1 here, is about the first unit vector, which is the X unit vector. So, how can you get CBA? Is the question. Well, you start with your initial reference frame, like that, and we said that we ended up with an intermediate reference frame like this. So obviously, the relationship between both reference frames is the rotation matrix C A prime A. Correct? From the previous lecture, just looking at the subscripts, you can easily determine that. Now, in the second step, we went from A prime all the way to A double prime through the rotation matrix A double prime, A prime, just again by looking at the subscripts. And finally, we obtain the final reference frame, starting from A double prime, and then the rotation matrix in that case has to be CB A double prime, like that. And again, this is only for the 3, 2, 1 rotation sequence. If I had given you another sequence, say 2, 1, 3, or 1, 3, 2, or any other rotation sequence, that would change what you plug in here, okay? The reason why I wrote down Z, Y, X is because the sequence was 3, 2, 1. 3 relates to unit Z, 2 relates to unit vector Y, and 1 was relating to unit vector X. And that's why I've been able to write it this way, okay? Now that you've established that you wrote down these equations, you can just substitute the sequence-specific rotation matrices in here and say that C A prime A, that's the rotation, the principal rotation that took you from the initial reference frame A all the way to A prime. And according to the sequence here, that was done through CZ. I'm going to say CZ, theta Z. Our C A double prime A prime, in our case, according to our sequence, we had established that that was CY, because CY was taking us from A prime to A double prime. That's what we're doing here. A prime all the way to A double prime. So that was CY, theta Y. And the last of the sequence was going from A double prime to B, A double prime to B through CBA double prime. And we said that according to the sequence, that was our CX theta X. Okay. Now, according to different textbooks you might be looking at, or journal papers or conference proceedings again, some people don't use CX, CZ, X, Y to denote principal rotations. Some people prefer to use the 3-2-1 numbering system instead. So previously I've described the CX, CY, and CZ in terms of their shared definition. Well, those could be replaced with C1, C2, C3. Okay, so CZ can also be written as C3 of theta Z. CY is same as C2. And CX is same as C1. Okay? Just two different ways of writing the same thing. In this course, we want to use both systems at different times. So I just want to make sure that you are comfortable with either way of writing principal rotations, okay? So just keep in mind that 1 is always X, 2, Y, and 3 is always Z. All right? So now that we've established that, again, going back to our initial question, how can we calculate CBA? Well, we know that CBA is a rotation matrix that takes us from reference frame A all the way to reference frame B. Now, based on what I wrote, I know that reference frame B in our sequence was obtained from A double prime, like that. But that A double prime as a reference system was obtained from A prime. So I'm going to say C B A double prime, as this is being replaced by that times C A double prime A prime from A prime, like this. But I know that A prime was obtained from A through C A prime A. I'm going to write down C B A double prime, C A prime A double prime A prime, and finally A prime was C A prime A times reference system A, reference frame, okay? So that is how you can go from A to B through a 3-step rotation sequence. Remember how we talked about merging rotation matrices together? Well, it works out here, right? The A prime subscripts cancel out, A double prime subscripts cancel out, and you're indeed left with C B A times reference frame A. Yeah. So it works out. So now that, well, essentially if you look at those two equations that were both for reference frame B, you can clearly see that CBA has to be equal to the multiplication of these three rotation matrices, correct? So, as per our sequence, we know exactly what each of these is equal to. CA prime A is our CZ, or C3, same thing. C A double prime A prime is our CY, or C2. And finally, our CBA double prime was equal to our CX, or our C1. So then I can say that because CBA is CBA double prime, CA double prime, A prime, CA prime A, I can easily substitute these with the sequence specific principal rotations, to write down that CBA double prime is my Cx, function of theta x, times CA double prime A prime CY, theta y, and finally my CA prime A was my Cx, function of theta x. And that will give you the answer for the rotation matrix that relates the orientation of reference frame B with respect to reference frame A. One thing to realize though is that this can easily be rewritten in terms of the other nomenclature system using the 1, 2, 3 as opposed to the X, Y, Z. So this could be written as C1, C2, and CBA double prime. CA prime A was not CX, sorry. That was our CZ, function of theta Z. Okay? 1, 2, 3. Now, this particular answer that you get to practically calculate CBA is specific to the sequence. I can't repeat that enough, okay? Because if the sequence would have been, instead of 3-2-1 rotation sequence, if it would have been a 1-2-1, you would have had a different answer for the right-hand side of this equation. But what is important is how can you go from sequence, in our case the 3-2-1, to practically calculating CBA. And hopefully through this example, for the 3-2-1 sequence specific, you've been able to wrap your head around the concept. One thing to realize, if you want to speed up the process and not go through all the steps to figure out how to calculate CBA, is to look at how things are organized on the right-hand side of that equation. So again, that was for the 3-2-1 rotation sequence, meaning that the first physical rotation was about the z-axis, followed by another rotation about the y-axis, and lastly, another rotation about the x-axis. Well, look at our result here to calculating CBA. This is actually the opposite order of the sequence, because CBA for the 3-2-1 rotation sequence is C1, C2, C3. So 3-2-1 sequence is 1, 2, 3 in terms of multiplying rotation matrices together. And this is something to pay close attention to, because I know some of you in the midterm or in problem sets will try to go fast and will say, okay, 3-2-1 sequence, 3, 2, 1. That's it. But this is totally wrong, because that will give you a totally different answer than the proper answer obtained by the proper sequence in terms of multiplying the rotation matrices together. So the key thing to remember here is that the sequence is related to, or the way you calculate CBA is related to the sequence, but in terms of calculation, you have to flip the numbering around to get your answer. Okay, let me give you another quick example to make sure that you all understand that. So we said 3-2-1 sequence. The meaning of that, and write it down on your piece of paper, is that the first rotation is about Z, second rotation about Y, and the third rotation about X. This is all we did. And we had established that in this case, CBA was 3, 2, 1, written backwards. Now, if you had a 2, 3, 1 sequence in terms of order of physical rotation, that would mean that CBA will be equal to C1, C3, C2. So 2, 3, 1 is the sequence. This is the order with which you need to multiply the principal rotations together. Another one. 1, 2, 3, let's say. Sequence would translate into a rotation matrix of 1, 2, 3, like that. Meaning that you go back to the lecture notes, pull out what Cx or Cy is equal to, remembering that this is the 3 by 3 with the 1 here, the zeros over here, and cosine of the angle of rotation. Your C2 is always what's written in the lecture notes, so that's this one, cosine, minus sine, cos, or whatever. And the last one is another 3 by 3, 1, zeros, cosine, cosine. And then you just multiply those 3 by 3 matrices together, and you would easily calculate CBA, okay? But the order with which you do the multiplication is crucial. And again, the easy trick to remember how to do it properly is to take the physical sequence, flip it upside down, and write the rotation matrix in the opposite order. So this is a 1, 2, 3 rotation sequence. This is a 2, 3, 1 rotation sequence. This is the 3, 2, 1 rotation sequence, and so on and so on. Okay, just to finish up the work for our 3, 2, 1 rotation sequence, we had established that CBA in our example was C1, C2, C3, meaning that you have to do this kind of matrix operation. So C1, I'm just going to use C for cos and S for sine to speed up the process. So cos theta x, sine theta x, minus sine theta x, and cos theta x. That's for my C1. Right? Principal rotation by the x-axis is always the same. It's always the 1 here, followed by zeros organized like that, and then cosine sine in this fashion. Now, that was C1. C2 is like that, with cos, this time theta y, minus sine theta y, sine theta y, and cos theta y. And finally, my C3 for the 3, 2, 1 rotation sequence is the last one here. And C3 or CZ is always the same. That's always 1 in third row, third column on the 3 by 3 matrix, followed by cos theta z, sine theta z, minus sine theta z here, and cos theta z. Now, all is left to do is to multiply these 3 matrices together and do it in 2 steps. First, multiply those 2 together. Then the result of those 2 multiplied with that one, or vice versa. Those 2 together multiplied with this. It's up to you. And if you do things properly, you're going to end up with cos theta y, cos theta z here, and here sine theta x, sine theta y, cos theta z, minus cos theta x, sine theta z, here cos theta x, sine theta y, cos theta z, plus sine theta x, sine theta z. That's only for the first column, so you see that the matrix in its analytical form is quite extensive. And then second column starts off the first row with cos theta y, sine theta z, and here you have sine theta x, sine theta y, sine theta z plus cos theta x cos theta z. Here, the third row of the second column, cos theta x, sine theta y, sine theta z, minus sine theta x, cos theta z. That's it for the second column of this 3x3 matrix. Thankfully, my board is large enough to write it all down on the board. And the last column is minus sine theta y, sine theta x times cos theta y. And the last entry is cos theta x, cos theta y. It's a big 3x3 matrix. To figure out the rotation matrix describing the orientation of reference frame B with respect to reference frame A. But as long as you know the axis or the angle of rotation about X, Y, and Z, you just plug these angles in that matrix and you're going to get the answer for the 3x3 numerical matrix that allows you to do the calculations. Okay? Keep in mind, though, again, can't stress that enough, that this is only the 3, 2, 1 sequence. All right? Any other sequence would give you a different answer at the end of the day, because the order with which you would multiply the principal rotations together are completely different, right? Here that was 1, 2, 3. But another sequence would be 1, 3, 1, 1, 3, 2, or 3, 2, 1, etc., etc. And the result would differ quite a bit. All right, so that's it for principal rotations and rotation matrices. Hopefully that makes sense for you. And now we're ready to move on to kinematics. Now, kinematics, hopefully you remember, refers to the study of motion from a geometrical point of view. So without involving any forces or torques and the derivations of the expression. Okay, that is related to the Coriolis acceleration equation you all saw in 2101 dynamics. As a heads up, we're going to rederive the Coriolis acceleration expression, but done properly this time around. But before we do so, we need to introduce another new mathematical tool known as the hollow operator, but one thing at a time, okay? First, let's begin this section on kinematics. And the first thing I want to talk about is angular velocity. So up to this point, everything was kind of static. We didn't involve any derivative of vectors, derivative of rotation matrices. Everything was done from a purely geometrical point of view or static point of view, where we're only trying to relate the orientation of something with respect to something else, or in other words, orientation of one reference frame with respect to another reference frame. All right? But now we're going to set things in motion. So to do that, we'll involve two reference frames. The first one is reference frame A, and we're going to assume that this one is inertially fixed. In other words, it doesn't move at all. It is set in concrete. And then I'm going to have reference frame B, which happens to have motion now with respect to the fixed reference frame. And we're going to assume that that motion is an angular motion or rotational motion. We're going to say that reference frame B is in motion with respect to our fixed reference frame, which is A. And that motion is an angular motion. It's not translating, it's only rotating with respect to reference frame A. So because the angular motion of B with respect to A is the only motion, I'm going to say that this is an angular velocity motion, and that angular velocity will be denoted by omega BA, and this is a vector, meaning that this is the angular velocity of reference frame B with respect to reference frame A. In other words, the angular motion of B with respect to the non-moving reference frame A. This is how we're going to denote things. Now, because we have reference frame B, that rotates about some arbitrary angular velocity vector omega BA, and this is with respect to reference frame A that doesn't move at all. So the motion here has to be seen from the inertial reference frame, okay? So if we say that B is in motion, it means that B is in motion with respect to A. But we can also say if we're sitting on B, we'll be seeing reference frame A moving around. So from that point of view, we can also say that A has a motion with respect to B, if B has a motion with respect to A. It just depends on which reference frame you happen to be sitting to observe the motion. So if that was angular velocity of reference frame B with respect to reference frame A, then we can say that we also have an angular velocity of reference frame A with respect to reference frame B. In that case, we're going to say that omega A with respect to B is in the opposite direction of B with respect to A, but of equal magnitude. So I'm going to write it like that. Okay? So now the question is, all right, let's go back to this situation where B is rotating in 3D space with respect to something inertially fixed. Well, if that's the case, how can we determine the derivative of the unit vectors that are comprising reference frame B? Or in other words, we are seeking expressions for Bx time derivative, By time derivative, and Bz time derivative. Okay? Now I'm not going to go through the entire derivation to give you that, but the answer to this is just taking the angular velocity vector omega BA and doing the cross product with Bx, By, and Bz. Okay? This is how, knowing how reference frame B is moving with respect to something fixed, how can we determine the rate of change of the unit vectors comprising this particular reference frame. Now, note here that I've introduced notation, which is the dot operator, and this is the inertial derivative operator. Inertial time derivative. Meaning that this is the inertial velocity along those vectors, if you will, due to the angular motion. Okay, now making use of those three equations, we know how we can compress those together using the vectrix notation. And specifically, I'm going to write down that the time derivative of the transpose of the vectrix is equal to angular velocity vector omega BA cross product with the transpose of the vectrix itself. I just took those three individual equations and condensed them into something more compact. That's all I did here, using the vectrix notation. Very important result. We're going to encounter that quite a bit in the subsequent derivations throughout the course. So make sure that you don't forget about it. Okay, the time derivative of a vectrix, or in other words, the time derivative of the individual vectors comprising a reference frame, is equal to the angular velocity vector cross product with the vectors itself, or the individual unit vectors. Okay, so this is an important result that's going to allow us to study the motion of spacecraft on orbit. Again, chapter 1 is all about building the tools and the building blocks that we need to analyze or mathematically model the motion of a spacecraft orbiting a primary body. There's quite a bit of new knowledge comprised in that first chapter, but be patient. We're almost done with it. But once we're done, we're just going to use those building blocks over and over again into building something more evolved, and that is the motion of spacecraft on orbit. Okay? Last thing I want to talk about is the additivity property of angular velocity vectors. So let's pretend now you have three reference frames. Reference frame C, B, and A, where reference frame B is in, obviously, angular motion. Everything we do now is rotational motion, is in angular motion with respect to reference frame B. And we also have, as per before, reference frame B, which is also in an angular motion with respect to our inertially fixed reference frame, which is reference frame A in our case. So if C is in motion with B and B is in motion with A, it implies that C is then also in angular motion with respect to A. Now, how could we determine the angular velocity of C with respect to A, where A is not moving, if we know the angular velocity of C with respect to B and B with respect to A? Well, that is super easy because there is this property inherent to angular velocity vectors that says that they can be added together. So angular velocity C with respect to A is equal to angular velocity of C with respect to B plus angular velocity vector of B with respect to A. You just add them together, head to tail. If you know the components, you add the X components together, you then add the Y components together, and finally you add the Z components together. So this is the additivity property of angular velocity vectors. And again, the trick to remember how they can be added together is just by looking at the subscripts. The B's are kind of next to each other, so they cancel out, and you're left with omega C A. All right. So now we have all the tools to go back and look at how can we calculate the derivative of a vector. And that will become handy when we get to kinematic acceleration, i.e. your good old Coriolis acceleration and centripetal acceleration. But first we needed to build a base to do that. So derivative of a vector in 1.4.2. Green tea again. Green tea is so good. All right. So in this subsection, we're going to look at vector u and two reference frames. Reference frame A with its three orthogonal unit vectors, and reference frame B, which may be oriented differently than reference frame A. Like that. Furthermore, we're going to say that reference frame A is our inertially fixed frame, whereas B we're going to say is moving with respect to reference frame A with some angular velocity denoted by omega B with respect to A as per before. So this guy is literally spinning around while this guy is standing still. All right. So the question will be, how could we determine the derivative of this vector u? Okay, so this vector u might be moving as well, and given the components of this vector in reference frame B, how could we determine the components of derivative of this vector in reference frame A? Okay, but first let's establish or express u in terms of its components in the moving reference frame, which is B. Nothing new here. Hopefully, by now you all know how to express a vector in terms of its components in a given reference frame. That's all we did. Okay, so now the question is, how could we get the time derivative of this vector? And not any time derivative, but the inertial time derivative. Remember the notation, the solid over dot we talked about earlier? This is the inertial derivative. What it means is that this is seen in reference frame A. Okay, well, to do that, all we have to do is to apply the chain rule to this very simple equation. So we're going to say that we're going to take the time derivative of the vectrix here, ub, plus transpose of the vectrix times the time derivative of ub, like that. Okay. Inertial derivative of u vector. Do you guys remember what this is equal to? Hopefully you do. Just covered that 5 minutes ago. The time derivative of the transpose of the vectrix was equal to the angular velocity vector cross the transpose of the vectrix itself. So using the previous result, we're going to say that this is omega BA, which is what is creating the motion in this case. Cross product transpose of the vectrix times ub plus transpose of the vectrix time derivative of the x, y, z component of this vector seen from the moving reference frame. Well, wait a second. Let's pay attention to this guy for a little while. So I said that this was the derivative of the components of this vector seen from the moving reference frame. Turns out that this is not the inertial derivative. The inertial time derivative is not that. Because the inertial time derivative better be expressed in the inertially fixed reference frame. I talked about that a minute ago. Turns out that this vector, because all this is a vector, is u vector, but it's not the inertial derivative of that vector, because if that would be the inertial derivative, the components would have been seen in reference frame A, like that. But that's not what we have. What we have is the time derivative of this vector, but seen in the moving reference frame. So to make the distinction between both, we're going to use the hollow operator. Oh boy, another new tool. Okay? So the hollow operator, by default, will always mean that this is a non-inertial derivative. Or in other words, the derivative of a vector expressed in the moving reference frame. Whereas the inertial derivative would always be expressed in the inertial reference frame, the one that isn't moving. All right, so then what? Okay, we're almost done here. So U, inertial derivative, would be equal to omega BA here, cross product with something. What is that something equal to? We have the transpose of a vector x times components of a vector U expressed in reference frame B. But that is just reference frame vector U, isn't it? Because we said it earlier, vector U can easily be expressed in terms of its components in reference frame B, like that. So this is actually just vector U plus the non-inertial derivative. Why do we know it's non-inertial again? Because of the subscripts. The subscripts tell us that this is expressed in the moving reference frame, which happens to be reference frame B. Reference frame B is not our initial reference frame, so this is the non-inertial derivative, like that. And I like to actually rewrite that equation by switching the order here. Just like that. Okay? So this is inertial derivative equal to the vector notation, equal to the non-inertial derivative plus the angular velocity vector cross product with the vector itself. Does that make sense? Hopefully it does. So think about it. So if there were no angular velocity involved with this reference frame, it would mean that this reference frame would be inertially fixed. The reference frame B would be inertially fixed, just like reference frame A. So you have reference frame B not moving, reference frame A not moving, such that this is the null vector, right? Cross product of two vectors has to be a vector, so that's the null vector. So in that case, the inertial derivative would be equal to the non-inertial derivative. In other words, the rate of change of this vector in terms of its x, y, z components, or the rate of change of that vector would be the same in both reference frames because both reference frames won't be moving, right? So inertial derivative equal to non-inertial derivative if that reference frame isn't moving. That makes a lot of sense. Now, it doesn't mean that their components would be equal because this might be oriented differently than that one. Still not moving, but just oriented slightly differently. But in terms of vector derivative, they would be exactly the same. Okay? This very important result, and I'm going to highlight it in red, and it's so important, and it deserves a different color. This is known as the transport theorem. Okay, so this again allows you to relate the non-inertial derivative of a vector to its inertial derivative in terms of vector form. Now, next up, we're going to have a look at how can we rewrite that very important result but not just in terms of vectors, but in terms of components of vectors. Because as engineers, we do like to be able to calculate things based on x, y, z components of n vectors. So that's what we're going to do next. Okay. I'm going to say here, still in the same subsection with just transport theorem in terms of components. Very useful. All right. So let's start with what we know, the vector form of the transport theorem. Non-inertial derivative plus angular velocity vector cross product with the vector itself will give us the inertial derivative of that vector. Now let's write down this in terms of components. Well, the catch here is that because we've introduced two different over dot symbols, the solid dot and the hollow dot, it means that we have no choice but to express this in the inertial reference frame, because this is what the solid dot forces us to do. It has to be the inertial derivative, so it has to be expressed in the inertial reference frame, which happens to be reference frame A in our example. So let's write it down. Just like that. Okay? This one here, U hollow dot, we don't have any choice again, because that symbol, the hollow dot symbol, forces us to write this derivative in terms of the non-inertial reference frame or the moving reference frame, which happens to be reference frame B. So let's write it down in terms of components in reference frame B then. Note that the hollow operator only applies to vectors. When I wrote this vector in terms of its components, I still use the solid dot component on the components. The solid dot operator on the components here, all right? As I wrote down previously, I believe in this part of the board, U hollow vector is equal to vector xb, because hollow means non-inertial, and that is our non-inertial reference frame. But the derivative of the components is just the standard first order differentiation. Take the current xyz components minus the previous one, divide by delta t, and that will give you the xyz derivative, okay? But again, this only means that we have to express it in the reference frame B, the non-inertial reference frame, yet we use the solid dot on top of any matrix. Something like that does not exist, okay? In other words, solid dot versus hollow dot only gives us an indication, do we use reference frame A or reference frame B? Hollow dot, non-inertial, boom, reference frame B. Solid dot, inertial, boom, reference frame A. That's all it means, okay? And the beauty about pre-recorded lectures like that is that you can go back to this explanation as many times as you want. Not only you can read what I wrote in the lecture notes, but you can also go back to this moment if that is confusing to you and watch it over and over again. And ultimately, after watching it 50 times, if you still don't get a good grasp on it, just send me an email or ask me the question during one of the Q&A live sessions. So let's keep going by writing all vectors in that expression in terms of their components, because this is what we want to do here, is to rewrite the transport theorem, not in terms of vectors, because we know what it is, but in terms of components. So let's keep going. Plus omega BA in terms of its components. Well, now here you have the choice. That vector can be expressed in reference frame B, or it can also be expressed in reference frame A. It doesn't matter, but because I'm going to try to write everything I have on this right-hand side of the equation in reference frame B, I'm going to stick to reference frame B for omega BA. So I'm going to write omega BA in terms of components like that in reference frame B. And then, well, if I write that in terms of reference frame B, I'm going to say that this is this, as per usual, vectors B transpose UB underscore. And actually, because I would have transpose of vectors B, I can actually take it out of that and write it like that. Now here, I cannot use the cross product symbol because the cross product is a vectorial operation. What I have to do instead is use the skew-symmetric matrix operator, which applies to components. All right? So never do cross product of two matrices. There's no such thing as a cross product of two matrices. Cross product is a vectorial operation, only applies to vector. How do you go from cross product of two vectors to skew-symmetric matrix of components? Well, we just covered that in the previous lecture. That was vector operation in terms of components, where we had looked at the dot product in terms of components and looked at the cross product in terms of components, and this is where we had introduced the skew-symmetric notation here. All right? So ultimately, I have this vector B transpose all over the place. I'm going to take it out, and it's like that, plus omega BA skew-symmetric, meaning again that I take this 3 by 1, which is omega BA, and construct a 3 by 3 out of it, with the zeros on the main diagonal, and I fill the rest of the matrix according to the lecture notes. Omega BA skew-symmetric times UB, like that. That gives me this on the left-hand side. So the equivalent of the transport theorem in terms of components is almost here. The only thing we have to do to finish this off is to take the transpose, dot product with the transpose of dot product, taking the dot product on both sides with the vectrix A, so that we can cancel out this term here and see what we have left on the other side. So dot product on both sides with vectrix A, because I know very well by now that doing so will cancel this term, because that's going to give me the identity matrix 3 by 3. 3 by 3 identity times a 3 by 1 gives me the 3 by 1. And I'll apply the dot product with vectrix A on that side as well. A, skew-symmetric UB. So now I have the inertial derivatives equal to, oh, what is this? Vectrix A dot product with transpose of vectrix B. Right away you know that this is rotation matrix CAB. If you don't, refer to what we saw previously in terms of defining rotation matrices and specifically their first use. Okay, so CAB times non-inertial derivative. Why do I know this is non-inertial? Because this is in reference frame B, plus omega BA skew-symmetric times UB, like that. And this, ladies and gentlemen, is the transport theorem, not in terms of vectors, which is what we had to begin with, but in terms of components, okay? Given the non-inertial derivative, or the components in B, how can we calculate the inertial derivative? Is through that expression. So this is transport theorem in terms of components. All right, so with that, we have pretty much all the tools we need to look at the acceleration from a kinematics point of view, so without involving any forces in the motion. So just from a pure geometrical point of view, or kinematical point of view, if you will. And that will be in section 1.4.3. We'll have a look at first velocity and acceleration, which was the first objective of this chapter, and that was to look at kinematics equations. The second objective will be to look at dynamics, and for that we'll have to involve Newton's laws of motion, but that will be for a separate lecture. Okay, so let's say we have a spacecraft in motion with a reference frame. Reference frame B, Bx, By, Bz. Reference frame B is itself moving with omega Ba, meaning that this is rotating with some angular velocity with respect to our inertial reference, which is reference frame A, Ax, Ay, Az. Let's denote the position of our spacecraft with respect to the origin of the moving reference frame as R. R vector is our position of the spacecraft. So our objective in this section is to obtain expression for the inertial derivative of the position vector, which happens to be the velocity vector, and also to obtain the double derivative, inertial derivative of the position vector, which is the inertial derivative of the velocity, which is simply the inertial acceleration. All right, so let's do it. We have all the tools to do it properly. So in terms of the inertial velocity, or the rate of change of this vector, seen from that inertial perspective, right? This is what our solid dot means. Given the rate of change of this position vector measured from this moving reference frame, well, all we need to do is to invoke the transport theorem, which says that inertial derivative is equal to non-inertial derivative plus what is causing the motion between the moving reference frame and the inertial one, cross product with the position vector itself, straight from the transport theorem. So that is our velocity equation from a kinematics perspective. That was easy. Now let's have a look at the acceleration from a kinematics point of view. Well, we can also apply the transport theorem to any vector. So let's apply it to the velocity vector. So we have the inertial derivative of the velocity vector equal to the non-inertial derivative of our velocity vector plus omega Ba cross product with our velocity vector. Okay? And here we're going to say where the hollow hold on a second. Oh, yeah. You know what? Okay. this r dot is also equal to velocity, the inertial velocity, correct? So I can write this as exactly the same thing as before. This is, okay? So the velocity is r derivative, inertial derivative, or just velocity itself. So that allows me to write that v hollow is simply equal to the hollow operator applied to this expression. Okay? So hollow operator on the left-hand side is v hollow. And here I have r double hollow plus omega BA hollow cross product position plus omega BA cross product R hollow operator, such that I can say, going back here, that the inertial derivative of my velocity is my acceleration equal to velocity dot equal to, now I have my V hollow, so that's my R double hollow, omega BA hollow cross product position plus omega BA cross product R hollow. All this is for this guy. Now plus omega BA cross product velocity vector. Now, we have to keep playing with that expression. So we're still looking for the acceleration, inertial acceleration, which is, again, inertial derivative of our velocity vector. So I'm going to rewrite it by then expanding what v is. So the first few terms are as per before. Nothing changed. A cross product R hollow plus omega BA cross product velocity vector. Go back here. Velocity vector was R hollow plus omega BA cross R. Because all of this, as per before, was my velocity vector, or just our inertial derivative to the transport theorem in the first place. Almost there. That means that my acceleration, that my inertial acceleration would be my non-inertial acceleration plus omega BA hollow cross product position vector plus omega BA cross product R hollow once, omega BA cross product R hollow twice. I'm going to say plus 2 times omega BA cross product R hollow plus omega BA cross product omega BA cross product position vector. Do I have all the terms here? Just double check. This, 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 and that. Yeah. And this, ladies and gentlemen, is the so-called Coriolis acceleration equation that you derived, or maybe didn't derive, but used in Dynamics 2101. This time done properly as it can get, okay? Now, if you look at this expression, the acceleration from the kinematics point of view, because as you can tell, there's no forces involved here. One thing you can notice is that here, 2 omega BA times or cross R hollow is the Coriolis acceleration term. And that's your omega BA cross product omega BA cross R is your centripetal acceleration. Et voila. All right. So that's it for today. We've achieved a great deal of progress in this lecture. We covered derivative of vector angular velocity, transport theorem, kinematics velocity, kinematics acceleration equation. That was a lot, but hopefully you guys have been able to digest most of it and wrap your head around the concepts. Next time, I'm going to have a look at dynamics equations, and to do that, we'll need to invoke Newton's laws of motion. Until then, keep it up, have fun. Thank you.